Okay, this video is going to continue on 6.2 where we're constructing a confidence interval for a population proportion. Let's go back and look at what we did in the last video. And we asked ourselves, what is a confidence interval for a population proportion? The confidence interval is just an interval with a lower bound and an upper bound. It gives us an estimated range that contains the true population proportion. Should say that we hope contains the true population proportion, or that we are estimated contains the true population proportion. So the confidence level, we're usually going to say C% confidence level is how confident we are that our estimate actually contains, how confident we are that our interval actually contains the true population proportion. This is a little more in depth than what we're saying here. Let's talk about why this is. I'm going to go over here and remember the sampling distribution from the last unit. And we said that if we meet certain criteria, that sampling distribution for p-hats, that's every possible p-hat from a population sample size n. Well, let's just do n there. N is the sample size, right? And that distribution is every possible p-hat from sample size n. And we said the mean of that, well, first that distribution, if we satisfy those conditions, we'll talk about it in a few moments, that sampling distribution is going to be approximately normal, that the mean is going to be the true population parameter p, and that the standard deviation for that p-hat is going to be equal to the square root of p times 1 minus p divided by n. And so now recall that sampling distribution contains every possible p-hat from every possible sample of size n. Every possible p-hat is contained in here somewhere. And so all the possible samples, all the possible sample proportions are contained within that distribution. When we do a 95% confidence level or confidence interval, we are estimating that approximately 95% of every possible confidence interval we can construct from the sampling distribution is going to contain a true population parameter p. So our confidence interval comes from the equation. We talked about this yesterday. P hat plus or minus z star times the square root. And since we don't know what p is, we would like to know what p is. That would give us a more accurate, but since we're estimating the population proportion p, we have to use p hat as a point estimate for that. So we're going to do the the confidence interval for the population proportion is p hat, the sample proportion, plus or minus the z star, I'll tell you how to get that in a minute, times the square root of p hat times 1 minus p hat, all divided by the sample size. And that p hat minus the z star times the square root of p hat times 1 minus p hat over n is the lower bound for our interval, and p hat plus z star times the square root of p hat times 1 minus p hat over n is the upper bound for our interval. We call that interval, or we call this part of that formula, this is equal to what we call our margin of error. I'm going to abbreviate margin of error as MOE. And so when you see like a political poll reported and says that 52% of people support candidate A with a 3% margin of error, what they have done is constructed a confidence interval using a sample proportion. And if they say 52% support, that's their p hat, and the 3% margin of error is this part of the sample, the standard deviation, the confidence interval. It's the Z star times the square root of 52% times 48% divided by n. That's where they get their margin of error from. That's where they calculate those margin of errors. And so what we're saying is if we take this confidence interval that has a randomly selected p hat and we add and subtract the margin of error, if we're doing a 95% confidence interval, we're saying approximately 95% of all of the confidence intervals we could construct with this sample size n and using this confidence level C would contain the true population parameter P. So this P hat that occurs here might have a confidence interval here. And this P hat that occurs here would have a confidence interval that occurs here. And this P hat that occurs here would have a confidence interval upper bound and lower bound. And 95% of all of those confidence intervals that we could construct will contain, approximately 95%, will contain the true population parameter P. So we have an interval that is our P hat minus our margin of error. And we have our upper bound is the P hat plus our margin of error. First thing you need to notice is that P hat is always in the center of that interval. So if you're ever given an interval and asked what P hat is, then you need to take the average of the upper bound and the lower bound because that's the number right in the middle. So P hat is always in the center of that interval. It's the sample proportion. We add and subtract the margin of error to get the lower bound and the upper bound. And what we're saying is 95% of those, because every P hat, recall, is in here somewhere. That's the sampling distribution, the distribution of all the possible P hats. And we're saying approximately 95% of these, 95% confidence intervals, will contain the true population parameter P. What that tells us is that we have a 95% probability. If we follow all of the conditions for inference, we have a 95% probability of capturing the true population proportion when we do a random sample, calculate P hat, and construct a confidence interval. If 95% of the confidence intervals contain it, and we do a random sample from all of the possible P hats, then we have a 95% chance of getting that P inside our confidence interval. So the confidence level is how sure we are that we catch the P inside our confidence interval. Oops. When do we use this confidence interval? All right, first off, let's say the confidence interval we want to use when we're calculating this is we're going to use what we call a one proportion Z interval. And when do we use that? We use that when we are estimating population proportion from a single sample. If you're working with two population proportions from two different samples, we're going to use a different interval. Right now, we're talking about one sample population proportion. That's what we're trying to estimate is a population proportion for some characteristic in the population. And we're going to do this with one sample. We're going to use a one proportion Z interval. And we'll give you the formula for that in a few minutes. As a matter of fact, I think we did that yesterday, what the formula was. Let's go ahead and put that in here too. That the formula for that one proportion, Z interval, is this right here. It's P hat plus or minus, this is a Z star, I cut this off of another website, times the square root of P hat times 1 minus P hat divided by N. We did that a few minutes ago on the thing. But a one proportion Z interval, this is the formula to calculate a one proportion Z interval. And you need to know those things. Let's talk now about the criteria for full credit when a free response question is asking you to construct a confidence interval. We got 4 things that we have to do, and we have to do them correctly. We have to supply sufficient information. We have to show enough work to show that we have satisfied these 4 conditions if we want full credit on a confidence interval for construction of a confidence interval. The first thing we have to do is name the appropriate interval. We're doing confidence intervals right now for a population proportion from a single sample. And we're going to call this a one proportion Z interval. When you're asked to construct a confidence interval, you have to name the interval. Now you can do this by name or by the formula. If you write the formula down without the name, that will suffice. My suggestion to you, however, is to write the name and the formula. We're going to do so many different things with the formula. They're going to ask you multiple choice questions that involve your understanding of the formula, that you need to be familiar with the formula and how to use it, and how to construct a confidence interval with it. So we're going to write it down a lot. And I suggest that you write it down whenever you're constructing a confidence interval. You'll become more familiar with it. You'll become more flexible with it, and you'll be able to identify answers to like multiple choice questions that they use to explore how well you understand what a confidence interval is and does. So we're going to name the appropriate interval. Then we're going to check the conditions for inference. You should be familiar with these conditions because these are the same conditions that I beat into your heads with the sampling distributions in the last unit. We need to make sure we have a random sample. We do a random sample so that we try to avoid a biased estimate. A random sample is more likely to generate a non-biased estimator. So the random sample is the first condition. A lot of times you'll be given it's a random sample, but you still, when you're checking conditions, you just state that you know this is from a random sample. The next thing we're going to look at when we're doing a population proportion, an interval for a population proportion, we're doing a one proportion Z interval. We want to make sure that N times P hat is greater than 10, and that N times 1 minus P hat is greater than 10. We did that for our sampling distribution. Recall that that guarantees the shape of the sampling distribution will be approximately normal. We need that to construct this confidence interval. And the last thing we're going to check for is the size of the population versus the size of the sample. We want N to be, little n, be less than 10% times the size of the population. Sample size needs to be less than 10% of the population, or you could say 10 times the sample size should be less than the population size. And you saw in the last unit how we reference that. We'll do that when we do examples in here. So we have to name the appropriate interval. We have to check conditions for inference. So we have to show work that says we know these things are true. Clearly state them, or you won't get full credit. It's just that simple. Then we're going to perform our calculations. This basically means that we're going to plug in, let's state our confidence level first. We're going to run out of room here, so I'm probably going to, I'm going to move this over here so we get some more room. State our confidence level first. Then we're going to plug in P hat, Z star, and N into the formula. And we are going to give our answer as an interval. You know what? I made new slides for all this stuff, so I wouldn't have to do all this on here. So we'll do that in just a second. Sorry, I'm not adept at making these videos yet. Perform calculations, and we're going to give our answer as an interval. That's going to look like our lower bound and our upper bound. And the last thing we're going to do when we're creating a confidence interval is we're going to make our conclusion in context. This is imperative. It's an essential part of getting all the credit for the confidence interval. So let's look back again. We're going to name the interval. See, I made the slides. We're going to do a one proportion Z interval. when we have one sample and we want to estimate a population proportion, we can name it by its name, one proportion Z interval, or we can use the formula. Once you write that formula down correctly, you have named the interval, but I would suggest you do both. Become familiar with it. The more you do it, the better you will get. Then we're going to verify the conditions for inference. A random sample. We're going to make sure that n times p hat is greater than 10, and that n times 1 minus p hat is greater than 10. Check these. Show the work that shows you know these. Don't just write n times p hat greater than 10. Plug in the numbers and show them. N times p hat equals whatever number, 28, which show that's greater than 10. Show that you know what all this stuff means. Put it in the context of the problem. Use the numbers from the problem so that you're showing your work and they understand you know exactly what you're talking about. And the last condition is for independence, that n is less than 10% of the population size. The sample size is less than 10% of the population size. Those are the conditions for inference we have to verify if we want full credit. Next, we're going to perform our calculations. So we're going to state our confidence level. We're going to plug in p hat, z star, and n to the formula. And we're going to state our answer as an interval. Lower bound and the upper bound. Those are what we have to do to perform the calculations. And then finally, criteria for full credit is our conclusion and context. This statement, if you write this statement this way, you can say it in other words that mean the same thing, but if you use this framework for the statement every single time, you'll get credit for the conclusion and context. So once we create our interval, our conclusion and context will be, we are, and then we're going to plug in. When I write these statements that you're going to have to plug stuff in, I will put in brackets what you plug in for that particular problem. Everything else is pretty standard, or is standard, but what's in the brackets is what you plug in. We are, C is our confidence level, so we say we are C% certain the true population proportion of, here's where we put in context, whatever we're dealing with. It could be frogs that eat flies. It could be eggs that hatch. It could be fruit that goes bad in the grocery store before it sells. It could be the number of, or the proportion of people who support a particular political candidate. It could be whatever the context of the problem is. You have to type that in here, or you have to put that in here. You have to state we are C% certain the true population proportion of, and then whatever in context, whoops, is between. You're going to put your lower bound and your upper bound. These are both proportions. That means they should be between 0 and 1. So we're C% certain the true population proportion of whatever in context is between the lower bound and the upper bound. That's the conclusion and context statement. So in summary, we're going to use a one proportion Z interval to estimate a population proportion from a single sample. And for the criteria for full credit, we have to name the interval we're going to use by name or formula. We have to show that the conditions for inference, verify conditions for inference. We have to perform calculations. Then we have to give our conclusion in context. Now, let's talk a little more about what this confidence interval is. Recall, I meant to show you this. And I forgot, like I said, I wrote this simulation to simulate confidence intervals. And what this does, I'm going to put one trial here to start with. Z for a 95% confidence interval is 1.96. I'll show you how to find that in the next video. But the Z is 1.96. And so what this is going to do, it's going to take a population of 1 million elements, and 100,000 of them are going to have the characteristic that we're looking to measure the proportion of. We're going to do a sample size 50 just because that makes nice numbers to deal with. And what this is going to do is it's going to run however many trials I tell it up here. It's going to construct that many confidence intervals. So down here, I set my margin of error equal to Z times the square root of, I did P. I need times 1 minus P. Divided by sample size. I'm not sure. Oh, because this is for different samples. Okay. Different successes inside here. This recalculates P. This should be P hat. We already did that. Sum P hat. Oh, no, it's resetting it after it goes through the loop once. Okay, that's what that's doing. All right, so anyway, this is going to generate a confidence interval. So I'm going to run this one time and show you what we're doing. We know the population proportion is 10%, 100,000 divided by a million. And it's going to do a confidence interval. And this one came up with a confidence interval from negative 0.003 to 0.163. So that tells us that what we would say from this confidence interval, if we did everything, all the 4 criteria for credit, the conclusion statement would be we are 95% confident, because we did a 95% confidence level, that the true population proportion of whatever the characteristic is that we're trying to do here is between negative 0.003 and 0.163. That's the conclusion statement. Now, what I want to show you here by simulation is that this is a 95% confidence interval. It means that we'll expect to capture, if we did this a lot of times, we will expect to capture the true population proportion that we know in this case is 10%, about 95% of the time. So I'm going to change the number of confidence intervals we create to 10 and run this. And this time we ran 10, and all 10 of them contained the true population proportion, 10%. Now these were getting a little close. There was a 12% there, 14% here. They were getting a little close. So let's see that it was 100% of the intervals contained P. Let's go and up this to 100 confidence intervals and run it. This time, 97% of the intervals contained it. Let's see if we can find one that did not and see where it's too high or too low. We did 100 intervals, so 3 of them should not contain it. They'll either be all above 10%, the lower bound will be above 10%, or the upper bound will be below 10%. Well, somewhere in there. There's one that barely caught it, 0.09. Let's see. If I put this in a spreadsheet, there's another one that barely caught it, 0.09. If I put it in a spreadsheet, I know we could find it, but right now it's kind of hard to scroll through here and find it. But this adds up the number of times that it contains it and the number of times, and calculates the number of times, or the percentage of times that it contains it. and it said 97% of the intervals contain P. Let's try it one more time and just run 1,000 confidence intervals this time. This is free software, so I can't run 10,000 like I would like to. But now we see 97.1% of the intervals contained it. We could do it again. And 97.5% of the intervals contain it. Yesterday, I was getting some pretty good numbers where it was close to 95%, 96.7%. But it's approximately 95% of the intervals will contain it. And that's how we set this. That's an example of what we can do here. Now, if you are going to, we'll do this on the next video. That's basically 6.2.